We go on with the third lecture by Antti on denormalization.
Okay, just to remind you what we started to do last time, introduced this renormalization operation in statistical mechanics, which was coarse graining and scaling, and then we argued that sort of to understand critical phenomena, this is a good idea, and we transformed the problem of trying to figure out behavior of correlation functions to trying to figure out how these Hamiltonians, which give the probability distribution, so the spins, how they evolve under this. So to solve the problem of infrared behavior was to understand what happens when you are given some model, what happens to some Hamiltonian, what happens as n goes to infinity when you iterate it many times. Okay, and then we had this picture that if there happens to be a fixed point of R, then you get a nice picture of sort of the critical theories being on the stable manifold of the fixed point. So now I want to talk about the quantum field problem, which is related to the unstable manifold of the fixed point. So let's go with that. So remember, quantum field theory for us is just a probability measure on S prime, and suppose somebody gives you such an object. Then let's see how we would look this picture there. So let's define something which is called effective field theory, something where you sort of again do coarse graining. So let me denote by b n of x. So if I take x on a fine lattice, so here, okay, e to the minus n of zd. So let's take a cube with center x and side L to minus n. So that's bn of x, and then there's coarse grain. Let's define the field. Let me call it phi n of x, where x is now on this lattice, which is just the average of the field in that cube. Okay, just take the average. That's the volume. So that's a lattice field, okay? So let me call nu n the law of it. Okay? So this we call the effective quantum field theory on scales bigger than or equal to L to minus n. So you forget everything what happens in the short scales. Okay? And you can also, let me call nu n and lambda, where lambda is some box. Well, it's just RD, where you restrict this thing. The law of this guy restricted to lambda. Okay, so this is of course now a finite dimensional object. So that I should be able to write as e to the minus some s, and let me call it also Sn comma lambda of phi, just the Lebesgue measure. Okay. So this thing we call the effective action. Okay. Okay. So what are these things? Okay. So to understand the measure nu, it's the same thing as to understand all these effective actions at different scales. So to connect it to that picture, we should go to the dimensionless variables. And what was that? Well, you introduced the lattice field where the x is in unit lattice, and with the usual formula, L2 minus an of this guy computed at L to power L to minus n x. Okay, so that's the definition. And then how are these guys now related? Well, it should be obvious. Phi n minus 1 is just CL of phi n. And if you want the picture, so here is L to minus n minus 1 cube. I'll divide it into L to minus n cubes. So the phi n lives here, and the phi n minus 1 lives in this big cube, and then once you blow it up by L to n, you get this picture. This is L, and this is 1, and that's where phi n and phi n minus 1 live. Okay, so phi n is here, and phi n minus 1 here. Okay. So then, of course, you can write the law of phi n. So just this in the dimensionless variables, and this we can call Hamiltonian. Put it like that. Dummy variable, and this is phi. And then these guys are related by the renormalization group transformation. Just H. If you reduce the scale, increase the observation scale, then you get this relation. Okay? So the summary of this discussion is that given a quantum field theory, you can look at it different scales, you get these effective actions, and once you look at them in the dimensionless variables, they are related by this renormalization group transformation in the following way. If you renormalize m times something which describes you at scale L2 minus n, you get the thing which is on scale L n minus n. Okay? That's, of course, there's nothing there except just changes of variables, but it's a useful thing to connect these two pictures. And let's see now two ways to look at that. Of course, our problem was not that we have a measure nu. We don't know that. We want rather to start with some statistical mechanics and some candidate thing for nu, and then construct nu. Okay, so one way to do that then is to do the scaling limit. Okay, so what would that be in this picture? Well, suppose we are in the situation that we have a fixed point in statistical mechanics. Okay, then I can introduce a cutoff field. Let me put it upstairs now to remember that we have a cutoff here. So this is something living on a fine lattice, and I define it again with the eternal formula. And let's put phi at L2 n x, and let's take the integer part. Okay, so here is the lattice field. I look at it at long scale and multiply it by something. And let me call nu n the law of this. Okay? Scaling limit is just so the scaling limit nu is the limit of this thing as n goes to infinity, if it exists. Okay. Concretely, it says that it tells you that the correlation functions of the scaling limit are given as limits of n going to infinity, L to power n a n, is from 1 to n. Well, let's put a k. You take the lattice field and you look at it at L to power n x1, and look at it at the fixed point. Okay, you just look at long distances and scale. All right. So suppose that exists. What are the effective actions? So what is Hn? The answers?
You haven't explained what little a is, or have you?
No, little a is a parameter which, but my question is what is Hn? Well, it's just H star for all n. Okay, so if you take the scaling limit, then its effective actions are just the same guys once you go to the dimensionless variables. And this is a scale invariant quantum field theory, so its correlation function scales exactly like that, and is also once this have the reflection positive the property, this is a conformal field theory. Okay. Okay, but that's a particular example. Yesterday there was discussion what is the difference between scaling limits and continuum limits. So let's look at slightly more.
You're right, of course, except it's only scalings by factors powers of L, presumably, in the way you set it up.
The way I set it up, yes. But nothing, I can set it up in a different way. And a posteriori, of course, you expect that it doesn't depend how you set it up. Okay, so continuum limit. Okay, so what is that? Well, what is that? That's a question. Find a cutoff thing. So find some action with counter terms, like what we already discussed before. So this is on L to minus n ZD. So try to find some cutoff action functionals such that the measures, corresponding measures, converge. Okay. Well, you can now translate it to this language what I had there. So this is cutoff, go to the dimensionless variables, so that corresponds to some Hamiltonian, right? And what should you then do with the Hamiltonians? Well, here is the picture. You should to prove that this converges is the same thing as to control all the different scale effective actions. So you would like to do the following, namely, from this you can of course construct now the effective actions at scale L to n, just like I did it there. So that corresponds to then some h n of n. And what is that? Well, from there I show that it's just this. You renormalize so many times. And then you are asking following question. Find a Hamiltonian depending on parameter capital N, so that if you renormalize it by so many times, it converges as capital N goes to infinity, something which is a nice Hamiltonian. So find this. Okay. All right. So what could you try to do? Well, one possibility is just that you take your Hn, just the H star. Okay. So that's what I discussed there. That's the scaling limit. Okay. Then all Hns are H star. You could do something slightly different by taking Hn a critical Hamiltonian, something belonging to the stable manifold of the fixed point. So you could take a critical guy, and then you repeat this story, and I leave it to you to show that from that you get nothing new. You get again Hn is H star. So you get the scaling limit. But then you could do something what you do in practice for the super renormalizable theories, and it's the following. So
This Hn goes to H star, or it is H star? It goes to H star.
Hn is H star. Hn is this limit here. I put here a critical guy, renormalize it infinite many times, I get H star. Okay. But the thing which you do in practice uses this picture, of course. So here is the stable manifold, and here is the unstable manifold. And let's do it like this. Okay, the flow lines go like that, like I drew there. So let's take here a bunch of Hamiltonians in my space. So here is some H, well, what should I call it? HM plus 1. And here is HM plus K. Okay, and now let's renormalize them. So let's look at how this flows. So this flows somewhere here. So here is R applied K times to H M plus K. Okay. I applied K times, so this should be something, well, somewhere, okay. Well, maybe I should draw this picture more putting this here. So, okay. So this goes somewhere here, somewhere here. Okay, so here is R, K, H, M plus K, etc. So these are approximations to something. So I try to choose this one parameter family which goes towards the stable manifold, so that the closer I'm here, the more, when I renormalize it more, I get something which, so here is R K minus 1 H M plus K minus 1. Okay, so I want these guys to converge to something which I call H sub M. I don't know why I put M there. Okay, and so then here I get H sub m plus 1, etc. So what do I get from this? So if you choose such a one parameter family, so that once you renormalize it like I do it in this picture, so that the limit converges, so it's this operation here, then where does the limit lie? The limit lies on the unstable manifold, okay? So if I do the continuum limit, if I succeed doing this, the effective Hn lie on the unstable manifolds on the fixed point. That's the picture. All right. So in some sense, we could say that critical phenomena. So critical phenomena of statistical mechanics are described by the stable manifold of a fixed point, namely all those Hamiltonians have the same critical phenomena, and the quantum field theories lie on the unstable manifold of a fixed point. Of course, an example of both is the fixed point itself, and that's this conformal, this scale invariant scaling limit. Okay, that's the end of the philosophy. Yes?
Why? I mean, you just take a direction just from, I mean, you go just to the stable and you turn to the unstable.
Yes.
Why not do the opposite? Is that going to the unstable to the stable?
I could start immediately at the unstable, of course.
And going through the...
No, then I wouldn't have, if, I mean, if I'm doing this because in practice I don't usually have much control what the fixed point is, but I understand some one parameter family. So you should think about this one parameter family in our language. This is just the Rm phi squared plus lambda, let's say lambda m phi 4, Ginzburg-Landau model. Okay? Plus gradient phi squared. This in practice will be, in our case, this is the one parameter family, and I'm trying to construct, figure out these numbers here as a function of m, so that this picture stabilizes. Okay?
So
I'm going to do it.
Only control in the direction. In the stable.
Well, you see that since you have to renormalize it infinite many times, you better take something which goes towards the stable manifold. Otherwise, you're going to escape to infinity. Okay? You have to do it infinitely many times. So then it's clear that you have to go towards the stable manifold. And in practice, you have some beloved models like this guy. Could also take an Ising model, okay, and do a similar thing to it.
This k over there, this you have Hn plus r to the power k.
Yes.
Of some Hn. So this depends on m somehow. You have to choose it in such a way that the limit exists in this direction somehow.
Right here, I just pictured. So
For
this
every m.
This is the capital N here.
Yeah.
Okay, so yeah, I don't know why I put an M there. I should have put an N there. Sorry.
Yeah, but you know somehow where you stop for each of this line, you have this bunch of points on your line, and somehow
exactly.
each of them you have to choose k in such a way that they have some limit.
Yeah, it's just the same picture as here. So I decided to call this K. I decided to call for some stupid reason that M, and then I was taking K to infinity. Okay, with M fixed. Yeah.
But Antti, you could also take this limit on the stable manifold a la Wilson. In other words,
On the stable manifold, that's here. Yeah, but then you don't get anything new. You get just the fixed point. But there is a difference between continuum limit and scaling limit. Okay.
but Wilson would take the continuum limit as a scaling limit.
Well, I don't know.
You'd go to
what Wilson would have.
epsilon. You did computation. You take the epsilon lattice,
Yeah, but I mean,
Transform that into a unit lattice at the
yeah,
expense of a very
yeah,
large
because
volume.
sure, if you want to construct a critical quantum field theory, then that's what you do. But if you, for some reason, want to construct a massive quantum field theory, sometimes elementary particles have masses, okay?
Yes.
And then you might want to do that, okay? So then that's the. Okay, so that's the general picture. Let me try to put some flesh to it by studying now how this picture comes at the Gaussian fixed point. And I could do it in the block spin formalism, but there it's a slightly messy to do in 1 hour, so let me try to do it in a slightly different, and this maybe or maybe not connects to, well, maybe it doesn't connect to what you're going to talk about, but let's see. So lattice is just one way to regularize quantum field theory. You can also use momentum space regularization. So let me do that. So we had the regularized, the Hamiltonians were on ZD, but I could take them on in the continuum as long as I put ultraviolet cutoff in some other way. Okay, so let me take a Gaussian measure with covariance, which is translation invariant all the time. But I take covariance which is really now x and y are in the continuum. But I put a cutoff here in the Fourier transform. And anything nice there, but if you want to think about something concrete, just put for instance this. Okay, so this cuts basically very strongly p less than 1, which you should think about being like the lattice. These things are smooth on scale 1. Okay. All right. In 2 dimension, you have to put a little bit infrared cutoff. It's in the notes. I won't go to it here. Then you can. I will still call the field with phi because it has unit cutoff, and then you could look at these Gibbs measures, which are just like before, where v lambda phi is what we had before, integral over lambda, and in our beloved model it's just this. And now it's a continuum object. Okay. So this is sort of another way to formulate the Ginzburg-Landau model, statistical mechanics. So what would the renormalization group be in this picture? Well, it's a very simple thing. You do it to this guy. Okay, so you take this covariance and look at it momentum space. So it's this chi p over p squared. So that's what it is. And decompose it into 2 pieces. One which is chi lp over p squared, and one which is chi p minus chi lp. Didn't do anything except that I added and subtracted something. So this has a cutoff p less than 1, so here p is less than 1 over L. Okay, so this and then here p is between 1 and 1 over L, basically, with that thing. Well, you can write that, of course, in Fourier transform. So you see x minus y, which is integral of e to the ip x minus y of this thing here. And you plug it in and make the changes of variables, and what pops out is the following. You get from this piece, when you make a change of variables, you get some power L here, and from there you get, but then you see that you get back the same C. So you get the L to power 2 minus D, C of x minus y over L for the first piece. And then the second piece is just something which I give a name. I call it gamma x minus y, and this thing here is a Fourier transform of that. Okay, so what can we say about these things? Well, C is given a rescaled version of itself, so nothing, there's a same thing repeating here. And then this guy has correlation length 1 over L. Why? Well, the momentum space integral is between p equal 1 and 1 over L. Okay, so that means in the lattice you go all the way to L in x space, so the correlation length is L. Okay, but think about L is here always order unity, like 2 or 3. But I want to keep it in the notation so that you remember that it's L. It can be. I don't want to call it 2. Well, if you have a Gaussian covariance written in terms of 2 covariances, these are both positive functions in Fourier space, and this gives rise to covariances. It means that the Gaussian field is the sum of 2 independent Gaussian fields. Let me write the other one. Let's call it phi prime. Independent. Okay, so that way I can define my renormalization group very easily in this formalism. I just integrate over the z. You should think about phi prime, the block spin, and z, a fluctuation in the block, but we are doing it in the momentum space instead of the x space. And well, if you have such a decomposition, then let's think about, for instance, the total integral. So integral e to the minus v of phi d mu c. Since the field is sum of 2 independent fields, I can write this as an iterated integral. So and let's give some name to this. So let's call it that phi is a scaled version of phi prime plus z. I call it SL is the scaling operation here. Then I have this. I first integrate over z with covariance gamma. And then I integrate over g mu c of phi prime. Well, let's call it phi prime. Okay. And then I can give this a name. This integral gives me some function. So let's call it e to the minus r of v. Sorry, phi prime. So our renormalization group is defined now as follows. I look at the perturbation, like the Ginzburg-Landau model of the Gaussian lattice Gaussian free field, this cutoff field, and r of the phi prime, and now I can erase even the prime. It's a dummy variable. Is minus log integral e to the minus v SL of phi plus z d mu gamma z. Okay. What should you think about this? Well, I said that this is a nice Gaussian measure. It has covariance which has order unity correlation length. So it should be the case that if I take local v, local like we had there, then it's mapped into almost local B. This is the original intuition of Wilson when he sort of came up with the renormalization group, or Kadanov. The idea being that coarse graining preserves sort of the natural class of Hamiltonians which are local. It preserves it because it sort of coarse grains and rescales so that things behave sort of like they were to start with. Now, we could go on studying this, and as you can imagine, there's a lot of headache in this almost word here. Okay, so everything when you start to hear real talks, not of this sort of fishy talk which I'm giving on rigorous normalization group, then all the headache comes when you start thinking about this, and maybe I come back to in the last lecture a little bit why there's headache, but now I'm going to cure the headache by changing the model a little bit. So this headache was very much in Wilson's head when he was doing it, and then he came up with something which he called an approximate recursion relation, which by Dyson was called hierarchical model. And after that, it has been an object of lots of studies, and it's actually very nice in presenting how this picture really works in practice without these almost problems. Okay, so I'm going to just use this same recursion, except that I'm changing the covariance so that it has sort of it's not this is sort of exponentially decorrelated in different points, but I take it completely decorrelated. Okay, so let's go to the hierarchical model. So now we are going again back to the lattice. So now x is in ZD, and I'm using exactly the same recursion as here, except that my scaling operation is slightly different. It's what was it there? L2 minus t minus 2 over 2. Right? Of phi at x over L. That's what we had. Well, if x is on unit lattice, then x over L is not. So let's take an integer part. Okay? And then let's consider the recursion where I have a lattice field and I decompose it into two pieces, namely this SL of phi. Okay? And let's call it prime, like I call it there. And then the rest. Okay? And let me take Z, a Gaussian field, which has the following property. So if I look at L blocks in my lattice, so the Z here and here independent. So whatever Z does here, it's independent of what it does here. And here, it should be like, think about this phi prime is really what we call the block spin. That's what I had here. So you take average of the original phi and rescale it by this power L to A. And this is what we had, the fluctuation there. In the true Gaussian free field, the fluctuation is slightly correlated. Here I take it completely decorrelated against the blocks. The only constraint being that sum over Zx being 0 in the block. So concretely, E expected value of zx and zy is just delta xy subject to this constraint. If you write that constraint, it turns out to be like this. You can check it yourself. Okay, so I can take such a recursion. Now, of course, there is a Gaussian field, namely the hierarchical field, which has such an independent decomposition. I'm not going to describe that at least now, but you get it just by iterating this decomposition. So there is a hierarchical field corresponding to this recursion. But what is so nice about this recursion is that now I don't have this problem. Namely, everything clearly, completely factors across the blocks, if you think about this transformation here. Because these are independent in different blocks. If I start with something which is local, I can decompose it into sum over blocks and then sum over the blocks. And then this expectation factorizes by independence. So, result. And the main point of hierarchical model is the following. If I take V, like here, I define like there. If V of phi is sum over x in some box lambda of phi of x, let's call it V of phi of x, then the renormalized V is also a local thing, just in a smaller box. Something which I call R of V phi of x. And R of V is given by the same formula. R of V is now a function of one real variable, okay? Phi here is just real variable. V is a function of one real variable. R of V is a function of one real variable, and it's given by this formula. Sum over x belonging to the unit block anywhere in the universe. So let's take that x over L integer part is 0, for instance. And here I have L2 minus d minus 2 over 2. Phi is just a number, not a function, plus z of x. And this measure is on R to power L cubed, L to power d. That's a simple nonlinear transformation. You take a function of one real variable, do this operation, and you get out a new function of one real variable. That's Wilson's approximate relation or hierarchical iteration. Sorry?
In which sense is it approximate?
Why did he call it approximate? Well, we'll see. Okay, it's actually capturing almost everything except the wave function renormalization. Okay, that's physicist answer. Okay, but we'll see later. But at the moment, let's just take it and let me study this. Okay, you see, there is something which is not in this model at all. There is no gradient of phi. So there are no irrelevant terms which are sort of gradients of the field. That's missing here. So if those play some role, then they are not in this model. And they play, of course, a role in some cases, like in QCD, for instance, the wave function renormalization is actually infinite. So, I mean, it requires non-trivial renormalization. But in most cases, it doesn't play much role, so this gives a rather good picture of the real thing.
I don't know what captures means. If you take, say, a 3D case and you study a fixed point of this,
yes, then it has a
fixed point of real equation.
This has
Any sense in which they're close by?
in 3 dimensions, they are in 4 minus epsilon they are close, yeah. Because the wave function renormalization eta is order epsilon squared, so you don't see it. This doesn't have eta. Okay, so in 3 dimension eta is actually non-zero. This doesn't have it in an interesting way.
You're missing out eta completely.
Let's return to that. I'm discussing that later. Okay. So if I discuss it now, then most of you don't know what I'm talking about. So let me rather postpone answering that question and study this a little bit first. Okay. At the moment, let's just think that seems to have something to do with the reality, and let's study it. Okay. So, what's the first thing we did in the philosophical picture? Well, we look at the linearization. So, what is the linearization of this? Well, it's just expanded to first order. So this I can write it as expected value. Well, so let's write it as sum over x, expected value. Let's put it like that. V of SL SL phi plus z of x in the measure gamma, in the covariance gamma. Okay, that's a linear map on functions. It's very easy to find the spectrum of this linear map. Namely, if I take a polynomial of nth degree plus lower order, then obviously this map is going to map it to a similar polynomial, namely, and you get what do you get? You get there are L to D terms in this sum. Let me write it like that, slightly misleadingly. So I get L to D, and then from SL, if I have polynomial order n, I get minus n d minus 2 over 2. Okay, so from this we see that there's a spectrum, eigenfunctions. Actually, you can find eigenfunctions. So they are polynomials of degree n, which have exactly these eigenvalues. They are actually Hermit polynomials in phi. You can do it in 3 and more dimensions, not in 2. In 2, this L is not diagonalizable. It's a sort of Jordan form, but let's not ponder on that more. So what are we supposed to look? These are the eigenvalues. Okay. Well, what were we supposed to do with these eigenvalues? Well, we were supposed to look at whether they are bigger than 1 or less than 1. So the ones which are bigger we called relevant. Which are the relevant? Well, you see that if you are in 4 dimension, for instance, okay, let me rather just list them and then look at them. So let me first in bigger than 4 dimension. Then you have only one relevant. Okay, so let's take examples. N equals 2, then I get L squared. Okay. N equal 2, I get L squared. N equal 4, I get L to power 4 minus D. N equal 6, I get L to 6 minus 2D. When we are more than 4 dimension, these are all less than 1, so there's only one relevant, phi squared, and the highest eigenvalue L squared. That's our mass term. Okay. When D is 4, well, then we have again this phi squared, which has last time. It's always a relevant one. But then we have also phi 4, which is marginal. It equal 3. We have again the phi squared with L squared, phi 4 with L to power 1, and phi 6 with L to power 0, so that's marginal. Okay, and then if I go all the way to 2 dimension, then every power of phi is relevant. So apart from 2 dimensions, I have very few relevant, only the phi squared in 4 dimensions. They're bigger than 4, only phi squared in 4, but then there is one marginal, and in 3 I have these 2. Well, what was our picture? Our picture was that the relevant ones are the ones which are relevant. So, and the rest should be sort of irrelevant for the purposes of critical phenomena, but also for the purposes of constructing the continuum limit. So what I want to do now is to go, well, that's the linear renormalization group. That doesn't, that's the starting point of the story. So what are we supposed to do next? We're supposed to do see what happens beyond the linear. In particular, every time we have something marginal, like here or here, it's likely that there will be something subtle or interesting, perhaps, happening. So let's look at that next. And let me now do it first the perturbative way again. But this is very different from the perturbation theory we did before. We are not going to do perturbation theory to the full model with one shot with all the divergences like we had before, but we are going to just do to this renormalization group map, this one thing, okay? So let's take our starting point, this Ginzburg-Landau model with these parameters R and lambda, and let's try to compute now beyond the linear order what is R of V. In the next lecture I will try to explain you why this gives the main result and picture, okay? But at the moment, let me just do it completely heuristically. Why expand this to second order? Okay, so minus log integral e to the minus sum over v of Sn. Well, let's just call it psi of x. Okay, that's what we are supposed to do, and so this equals sum over x, expected value of v of psi of x. Well, we are familiar already what perturbation theory is. The next order is minus half sum over x and y. Both run from 1 to L to d. Let me label the points in the block by that. And then I get the truncated expectation of v of psi of x, semicolon v of psi of y. It's exactly like we had before, except that we have just the finite sum here now. And then the rest is order v cubed. Okay? Well, it's obvious, this we computed, okay? So it's obvious that this will be now, again, a polynomial in phi, but now I can have a little bit higher terms. So I can just write it. This is a constant which we don't care about, and then it has some term which is of the same form as we started with. Put a half there. Then there is a lambda 1 phi 4 that we computed there already, but here I get also something like that. And then there is the rest, which let me call it just W1. And let's call this V1. Okay, and what is the recursion? So R1 is L squared times R. That's what we saw here in linear order. From here, I didn't look at what this lower order terms is, but there is clearly a lower order term. And let me just write. Let me give it a name. Just plus gamma 1 of R. Gamma 1 of times lambda. From here, if I expand this to this fourth power, I get a phi squared and expected value of z squared. So there is a number there. Then clearly I get something like, let me put it, gamma 2 lambda squared. There's even a gamma 3 r times lambda, and then plus something which is order lambda higher order. Let's say lambda cubed. Coming from here. What about lambda 1? Well, L to power 4 minus d lambda plus something which let me call b of lambda squared plus order higher order. And then finally there's this W1 which I'm going to ignore. I'm going to ignore it because if my plan is to collect here always the terms which are the relevant terms, and then this would be something if we had started with it. We started with W to 0 because we started with this initial condition. But if I did this iteration now, there would be some linear renormalization group acting on it plus high order terms, and what we expect is that in some suitable norm this is something which contracts. Okay, that's the irrelevancy. Okay, so for what I'm going to now, the calculations I'm going to do, I'm mostly going to ignore this W and just trying to explain this picture starting with this iteration here. And later we'll see was it interesting or not to have this W there. Okay, that's a very simple recursion. What are we supposed to do with it? We are supposed to look at the various cases. So we are supposed to look at more than 4 dimensions and find the critical point. We are supposed to look at the 4 dimensions and figure out the critical point and whether something happens with this phi 4. We are supposed to, then we go to below 4 dimensions. It turns out that there in the infrared we have a really interesting problem of finding a non-trivial fixed point. And then there is the ultraviolet problem of constructing quantum field theory, which is again a simple problem of this recursion. And okay, that's the plan. But I suppose it's a natural point to stop here and start with that iteration next time. And if you want to, instead of having lunch, you could read the notes and and see that there are nice there are explanations of what is the underlying hierarchical field, etc. I'm not going to discuss it here. Okay, thank you.
or you can ask questions during lunch. So we start again at 1:30.